Swayam Prabha. Digital India. Educated India.
And it's a very simple algorithm. So let me write the algorithm first. So let me call it preference elicitation algorithm. It's try to elicit the preference orders. These orders I am calling it preference elicitation algorithm. What it is? It's very simple. So for all pair of objects AI AJ, find the crossover point by binary search. Yeah, I am not writing the algorithm formally. Let me explain to you how it is working. So I have, so suppose these are my orderings. Sure, these are my n orderings, and I pick any two alternatives, any two object AI and AJ. I first query the first guy, first person. Do you prefer AI over AJ or not? So without loss of generality, let's assume that the first guy says AI is greater than AJ. Then I query the last guy. If the last guy also says AI is greater than AJ, then I know that everyone in the middle says AI is greater than AJ. I don't need to ask. Sure, everyone with me? Because of single crossing property. So let's assume that last guy says AJ over AI. Now let's, so this is 1 up to n. Now let me ask the middle guy, n minus 2th guy. Tell me, whom do you prefer? Who is greater, AI or AJ? So suppose it says that AI is greater than AJ. So if it says that AI is greater than AJ, then I know that everyone here will say AI is greater than AJ. And if it says AJ is greater than AI, then everyone below I know. So just forget the first two queries. Now for every query next, for every next query, you are sort of knowing the ranking of AI and AJ of half of the people. For the next query, then again you ask the middle of this span, maybe here, and again based on answer, another half you again know. So for every pair, so number of comparisons per pair is big O of log n. Clear? And there are only m square many pair, m choose too many pair. So total number of comparisons is big O of m square log n. So just compare it with what we had before. So this is versus big O of mn log n. So you can't say it is strictly better, it's little incomparable. If n is quite large compared to m, it's basically we are replacing n with m. So if n turns out to be large compared to m, then we have made an improvement. For our toy example, we had 10 restaurants, so m is 10 and we are around 30 people in the room, so n is 30. So for that example, we have made improvement. Oh, sorry. Yeah, I'm missing up a little bit. Yeah. So this is log n. Yeah, m square log n. Yeah, m square log n. Sorry. M square log m. Yeah, log m. Correct. N square log m. Correct. Yeah. Yeah. This is log m. Here I have written m. Actually, this is m. So this is an improvement if. So let me write improvement if say n is much greater than m. So not in our example, I think. Sorry. Yeah, n is the n is what? N is number of items, and this is number of people. Yeah, yeah, not in our example, but in some other example. Okay, but yeah. There is one sort of criticism about this algorithm is that algorithm makes queries all over the place, in the sense that in real life cases, if real people are involved, it makes much more sense to ask all the queries to one person at once. It's not that I ask one query. For example, I ask a query to m by 2th person, and then the next queries are not going to m by 2th person, and then after AIAJ is over, maybe then for some other pair, again it's the same person is getting asked, and again he is not asked for some more time and so on. So it's like more like we are accessing these oracles or people in a random fashion, more like random access memory. We can access any part of the memory. It's not sequential access. So in some applications, we may want these queries to be asked sequentially. So whatever queries, how many queries, what you want to ask, you ask to one person at a time. You don't bother her repeatedly. So yeah, question. Yeah, these also I need to change. Yeah, that's true. So, thank you. So, so elicitation for sequential oracles, sequential access. So these oracles, these persons, you can access only sequentially, and obviously this algorithm does not work. Yeah. Sorry. Yeah, that's true. So we have a proof that this is what you best can do. Of course, you have that mn log n, so that minimum of two those kind of things. But yeah, this is what you best you can hope for under this random access model. But for sequential model, you need to pay more. Let's see. How many of you know insertion sort? Just a show of hand. Insertion sort. Yeah, good. So so since some of you don't know, let me just explain what is insertion sort. Insertion sort. So it's often called card sort. Yeah. So it's that. Let me explain in terms of with numbers and with an example quickly. That suppose I want to. I'm given a bunch of numbers. Suppose I want to sort these numbers. What I do is that I go from left to right, and first I try to sort one number. So since it is one number, it's already sorted. Next, I want to move the window to right, and I want to sort these two numbers. Now, to sort these two numbers, I move 7 to the left. So this 7 and 9, and then and leave everything else as it is. 7, 9, 10, 1, 5. And now in the next iteration, I want to incorporate 10. Now 10 is already greater than 9, and I know that this part is already sorted. So I don't need to compare with any item on the left. So this is also sorted. In the next iteration, I go one more step and 1. Now 1 is less than 10. So and I keep on searching for the appropriate place where I should insert 1, and I see that 1 should be inserted left of 7, and there I insert. So I get 1, 7, 9, 10, and then 5 it is as it is. Now in the next iteration, I move my window and I want to incorporate 5, and I again by sequentially searching I find the appropriate place and put 5 there. So this is insertion sort. Okay, couple of observations regarding insertion sort. What is its worst case running time? N square. Because in worst case every item may need to be compared with all the items before. Suppose I want to sort the items in non-decreasing order, and the input is given in non-increasing order. In that case, that's the worst example. And so worst case big O of n square. Can someone tell me what is the best case running time? Yeah, best case running time is n. If the input list is already sorted, then yeah, whenever we move the window, only one comparison per iteration. So best case running time is n. Yeah, we are going to need this. Okay, now let's come back to our algorithm. If the persons can only be accessed sequentially, and here is, let me write the algorithm first and then let me explain. So so let R1 is the, say, ranking of oracle 1. So maybe for this thing use merge sort. What do you mean by use merge sort? Just run merge sort, and whenever you need to compare two items, just call the oracle. And we know merge sort takes n log n times, so the number of queries for this step is also n log n. But from the second step onward, don't do merge sort. If you do merge sort in every iteration, then you will go back to your n log n. So from the second time iteration, do more knife sort, that's the insertion sort. And I will convince you that insertion sort works much better here. So for I equal to 2 to n, Ri is ranking of Oracle elicited using insertion sort using with respect to R I minus 1. So in insertion sort, there is an input ordering, right? So based on which I am moving the window, the order in which the input is given to me. In this case, we don't have any input ordering. So from R2 onwards, I am saying that for R2, you pretend that as if R1's ordering, which you have already elicited, is your input ordering for your insertion sort. So, what is it again? Let's go slow. What does insertion sort do? Input is given in an order which may not be sorted, but it's in some order, and in that order I first look at the first element, second element, third element, fourth element. So it's with respect to this first element, second element, third element is with respect to the input order. So I'm saying that when you are eliciting the oracle's order for R2, use the R1's order as your input order when running insertion sort. When you elicit R3, use R2's order as your input order in the insertion sort. While eliciting R3, you already know R1 and R2, use R2's order. In general, when you eliciting ith oracle's order, use I minus 1th oracle's order as the input order and run the simple plain old insertion sort. Clear? I will show that for most of the cases we are in the best case, not in the worst case. In the best case, insertion sort beats merge sort, and we will be mostly in the best case if we do this thing, not mostly in the worst case. And that's it. This is for loop, and then output R1 to Rn. Sure. So now let's do the analysis. But before that, is there any question regarding the functioning of the algorithm? Does anyone feel that he can't or she can't code it? And you should be able to write a C code with this description. Sure? Okay, now let's do the analysis. For the first order, I need big O of n log n because I have used merge sort. For the second order onwards, let's divide the total comparisons into two categories. So here are comparisons. These are total comparisons, and you divide it into two parts. One is, I don't know, just calling it good. Another is calling it bad. What is good and what is bad? So in the ith iteration, if say AI and AJ are compared, and in RI Yeah. So suppose I have made a comparison. The algorithm has made a comparison in ith iteration between two objects AI and AJ. I will call this comparison a good comparison if AI and AJ are ordered in the same way in both Ri and Ri minus 1. Ri minus 1 is the ith I minus 1th oracle's ordering, and Ri is the ith oracle's ordering. And bad is otherwise, if it is not good. Bad is not good. We all know bad is not good. That means that AI and AJ has been compared in the ith iteration, and Ri and Ri minus 1 order AI and AJ differently. Sure? And now let us make this observation that number of good comparisons per iteration is big O of n. This is my first claim. If you just concentrate on good ordering, good comparisons, then the number of good comparisons in every iteration is big O of n. Why it is so? Let us see. So suppose use this color. So suppose this is Ri minus 1, and suppose this ordering is A1, A2, AI, AJ, and so on. Now, and in Ri also, I know that AI appears before AJ. There can be something else. This left side may be different, but I know AI appears left of AJ because it is a good comparison. Now, because insertion sort, because it is an insertion sort, so when AJ will get compared, so in the jth iteration AJ will get picked, and we will keep comparing with all the items on its left. That is the insertion sort, and find the appropriate place, isn't it? In insertion sort, we pick one item at a time and keep comparing two items on the left to find an appropriate place. Now, AJ will be picked at the jth iteration. By the time all the first j minus 1 part is already sorted, isn't it? Now, if AJ gets compared to AI, that means the last comparison, whoever is here just after AI, AJ is greater than that. So, if this is x, then it must be that AJ is greater than x. If AJ is less than x, then the comparison would have stopped there. We are keep searching for the place for AJ. It's just plain old insertion sort. You just keep comparing from AJ. It's like here in this example. So in 1, you first compare with 1 with 10, and if 1 is more than 10, then the algorithm the comparison has stopped there. It won't go beyond. Because 1 is less than 10, it gets compared with the next item. Because 1 is less than 9, it gets compared with the next item, and so on. Same thing goes here. So because AJ gets compared with AI, that means that's why it got compared with x, and AJ must be greater than x. Yeah, and we already know AI is greater than AJ because it's a good comparison, and we know that AI is greater than AJ because it is a good comparison. AI and AJ are ordered in the same way in Ri minus 1 and Ri. So, two crucial observations. AJ is greater than x because AJ gets compared to AI. If AJ is less than x, then we already know AJ is also less than AI. This comparison wouldn't have been made. Because AJ got compared with AI, AJ is greater than X, and because AI and AJ is a good comparison, that means they are ordered in the same fashion in Ri and Ri minus 1, and that means that AI must be greater than AJ. So, after this comparison for AJ, we know the place where AJ should be inserted. It should be inserted between AI and X, isn't it? AJ is less than AI and greater than X. So, in that iteration, searching for place for AJ has stopped, and the observation is that for every for every item there is at most one good comparison. For every item there is at most one good comparison per iteration. Isn't it? Because once you have a good comparison, the search for its appropriate place in the insertion sort you have already found. So, for every item there is only one at most one good comparison, and there are n items. So, there are big O of n, at most n good comparisons. You do not need big O of n also. Number of good comparisons per iteration is at most n. Sure? Question? Anyone want me to repeat this part? It is just that in insertion sort what we do, we pick one item at a time and linearly search where it should be inserted, and the good comparison is defined in such a way that once it makes a good comparison, it has found its place where it should be inserted. That is the main observation, and that is why for every item there is only at most one good comparison, because once there is a good comparison for that item, you know the place where it should be inserted, and you do not make any more comparison for that item, and there are only n items. So, at most n good comparisons per iteration. So, total number of good comparisons is m minus 1 times n, because for the first voter we used merge sort, and for the rest m minus 1 voters, every voter can have at most n good comparisons. So, and there are m minus 1 of them, so m minus 1 times n. Everyone with me? So, we have computed total good comparisons of the algorithm for the oracle 2 to oracle m. Now, let us compute what are the total bad comparisons. But before that, any question? Yeah. Correct. At most n, yeah. Why am I writing exactly n? Oh, yeah, good comparisons. Yeah, sorry, yeah. At most n. Yeah, thank you. And it is actually, if you think about it, it is actually exactly n minus 1. For every item except the first item, you have to make a thing, or no, it can be less than n minus 1 also. Yeah, sorry about it. Yeah. Okay, so now we have computed total number of good comparisons. Let us compute total number of bad comparisons. I claim total number of bad comparisons. Let us compute total number of bad comparisons. Again, when we call a comparison to be bad, if Ri minus 1 and Ri and AI and AJ, suppose they are compared and they are ordered differently. So, suppose in Ri minus 1 AI is greater than AJ, and in Ri AJ is greater than AI. Right, and if they get compared, then we will call this comparison a bad comparison. Right, that's from the definition of bad comparison. That's how we defined, that's how we decided to call a comparison to be bad. But now I claim that once a pair AI and AJ has made a bad comparison, it can't make any more bad comparison because of single crossing property. Again, once a pair of objects AI and AJ makes a bad comparison, it can never make another bad comparison, because all the oracles down here, everyone prefer AJ over AI, isn't it? And till Ri it's already been elicited. So look at the first time when a pair AI and AJ makes a bad comparison. From that point onward, everyone orders AI and AJ in the same way because of single crossing property. This single crossing property, the ordering of AI and AJ can toggle at most once. Sure. And so we are done. So then what are the number of pairs we have? N choose 2. So total number of bad comparisons is less than N choose 2. So in total number of comparisons is big O of N choose 2, which is like N square plus Mn. Yeah. So here again, if M is large, M means the number of people is large, which is the case in our example, then so what is the average number of queries that you are asking? If you divide by M, it is N by M plus N, and if M is large compared to N, it is like you are asking N number of queries per voters, which is a saving from N log N. Sure. Question? Now again I'll throw you another puzzle. So here we use that we know the single crossing order. So this ordering of the oracles with respect to which the orders are single crossing is already known, and like voters are coming in that order only. Suppose that this order is known, but voters are not coming in this order. Voter is coming, vote not, or people are queried in some arbitrary order. Think of people going to a election poll and casting their votes. They are not going in a single crossing order based on their salary. They are going based on their convenience, their arbitrary order. And again, all the queries to him may be asked at once in the sequential access model. So is the problem clear? Although there exists an order with respect to which the input orderings are single crossing, but the the people that we are accessing is not single crossing order. Then your bad cost argument that for every pair you encounter only one bad cost is not valid at all, because the order that in which you are accessing the people is not single crossing order. But let me keep this as a puzzle or exercise. You can tweak that algorithm little bit and get the similar kind of guarantee. I think there the guarantee you may get n cube, but that mn term will be same. It will be like mn plus n cube kind of thing.